All right, so today we are covering chapter 11, which is all about ANOVA. Okay. ANOVA stands for Analysis of Variance. And so it takes the AN and the O and the VA for ANOVA, right? And so if we're going to talk about variance, it makes sense to just kind of review the definition of variance. And we can say it can be thought of as the quote unquote average squared distance from the mean. And where we see, large variance, that indicates that the values are in your data are spread out. And small variance means your values are similar to each other. Okay. And so what the big idea of this chapter is that we're going to try to see if we can explain some of the variance, the variance in a variable, right? So we pick one of these variables in our data set and we see, okay, the values are spread out or they're not so spread out or whatever it is. And we're going to try to explain some of that variance with another variable. Here, you know what, let me also just throw in the formula for the variance, right? So the variance, which we call S squared, the sample variance. The sample variance is given by, you take each individual value, subtract off the mean, you're going to square that difference and divide by n minus 1, right? So you square that difference, add them up. And if we were to divide by n, it would just be the average square distance from the mean, but we're dividing by n minus 1, and so that's why I put average in quotes, okay? And so this is kind of our big idea of the chapter. Okay. Can we explain some of the variance with another variable? We'll say, can we explain some of the variance in one numeric variable with with another variable, and the other variable will be categorical. Okay. And we've done something similar to this when we did t-tests. So when we did t-tests, we were basically asking if we can explain some of the variance in one variable with another variable. The basically, when you did a t-test for independent groups, not the paired t-test. Also tries to answer this question. Okay. Looks at a numeric response. And quote unquote explains some of the differences by using a grouping variable. And, for example, you might conclude group 1 has a larger mean and group 2 has a larger mean than group 2. Okay. And with ANOVA, we can basically do the same thing, except we will not be limited to just having 2 groups. Okay, so we can have, you can do it with 2 groups, but we can also do it with, say, 3, 4, 5, however many groups we need. Okay. All right, so this is 2021 summer week 5, Tuesday 1. All right, so let's try an example here, okay? But let me just talk about, let's say we wanted to compare the means of, say, 4 different groups, okay? Means of, basically 4 different groups. Okay, and so basically we would have we have random samples drawn from each of the 4 populations. Okay, if I asked you to do this right now, before we covered today's lesson, you might try to take a stab at this question by doing just a bunch of t-tests. And I think that would be a very reasonable approach, right? So if I didn't teach you today's lesson and I said, I want you to do this thing, I want you to compare the means from 4 different groups, you might say, can we just do a bunch of t-tests, right? So I just do a bunch of t-tests and just basically we would compare 2 groups at a time. Okay, so if you have 4 groups and you're comparing 2 at a time, you would end up having 6 comparisons, okay? 4 groups will be 6 comparisons, okay? And you would have, so these would be all of your different null hypotheses. Let me just list them off. So let's do test 1. Test 1 would have the null hypothesis. You would compare mean 1 equal to mean 2. Test 2 would be mu1 is equal to mu group 3. Test 3 your null hypothesis would be mu1 is equal to the mean of group 4. You have a total of 6 of these things. Test 4, you would check mu1 equal to mu3. Test 5, you would check mu2 equal to mu4. And test 6, you would check mu3 equal to mu4, okay? And this would cover basically every possible pairwise comparison, right? Every two possible combination of two groups, this would check them all, okay? All right, so I mean, it's a little bit tedious to do 6 of these things, but that's not the inherent problem, okay? The problem with doing a bunch of two-way comparisons is not that it's more work, okay? It is more work, but you know, with the assistance of a computer, it's like marginally more work. It's not too bad, okay? Can anyone guess what the inherent problem is with doing a whole bunch of comparisons? Not that it's more work, but there is an inherent problem with this. Anybody want to take a guess? And this is known as the problem of multiple comparisons, okay? Okay, so the problem of multiple comparisons is not that it is more work, okay? It is a little bit more work, but a little more work we can deal with. We don't mind that, okay? The problem of multiple comparisons is that we dramatically increase the risk of type 1 error, okay? So let's think about this. I'll just say we greatly increase the risk of type 1 error. So what is type 1 error? Type 1 error is false positive, right? And that's rejecting the null hypothesis when it is true. Okay, and so if we did for one test, what is the risk of type 1 error? The risk of type 1 error is equal to what? Oh, you guys are breaking my heart. There we go. Thank you. Thank you. For one test, the risk of type 1 error is equal to alpha, right? Our chosen alpha. Okay, so, you know, maybe say 5%. Okay, so we do one test, our risk is 5%, right? Okay, so, you know, it's kind of just like, I don't know, you play a game or something, and it's like, you know, you're every time you do it, there's a 5% risk that, you know, you're gonna make a mistake, right? You're gonna get out, right? And it's kind of like you're pressing your luck, right? Every time you do it, you know, you got a good chance of winning, but there's like a 5% risk of losing it all. Okay, I don't know, maybe losing it all is a little bit too dramatic, right? But it's like you can imagine a game show where it's like you're spinning a wheel, and one of the wheels, one spot on the wheel is like bankrupt, right? So it's like Wheel of Fortune. You got a whole bunch of things where you win money, but then one of those spots it says you lose all your money. Okay, so you spin it once, not a big deal. But then if you spin it a whole bunch of times, what's your cumulative risk of hitting the kind of the bankrupt space or blowing up in terms of committing a type 1 error? Well, it keeps going. Every time you do another test, you're running another like 5% risk, right? So one test, you can say, all right, I only have a 5% risk. but then you do 2 tests, 3 tests, 4 tests, 5, 6 tests, okay? What's the probability you're going to emerge after 6 tests completely unscathed, right? And the idea there is like, well, you're quite likely to commit a type 1 error, right? So so for one test, the risk of type 1 error is alpha. If you do a whole bunch of tests, okay, your risk of type 1 error is much greater. So there's a great little comic. Let me see if I can find it here. There it is. So this is, I don't know if you guys ever read XKCD. It's like a little nerdy comic strip, but it's a web comic, and they do a bunch of science stuff. I think the author used to work for NASA. Okay, anyway. All right, so the comic goes like this, right? Jelly beans cause acne. Scientists investigate, okay? And then the scientists come back and they say, we found no link between jelly beans and acne, the p-value greater than 0.05. And they go, okay, that settles that. And then someone says, I hear it's only a certain color that causes it. So they say, scientists, and then they have to go and investigate this, right? So it says, we found no link between purple jelly beans and acne, okay? We found no link between brown jelly beans and acne, p greater than 0.05. We found no link between pink jelly beans and acne, p greater than 0.05. We found no link between blue jelly beans and acne, p greater than 0.05. We found no link between teal jelly beans and acne, p greater than 0.05. We found no link between salmon jelly beans and acne, p greater than 0.05. We found no link between red jelly beans and acne, p greater than 0.05. We found no link between turquoise jelly beans and acne, p greater than 0.05. We found no link between magenta jelly beans and acne, p greater than 0.05. We found no link between yellow jelly beans and acne, p greater than 0.05. We found no link between gray jelly beans and acne, p greater than 0.05. We found no link between tan jelly beans and acne, p greater than 0.05. We found no link between cyan jelly beans and acne, p greater than 0.05. We found a link between green jelly beans and acne, p less than 0.05. And they go, whoa. All right, we found no link between mauve jelly beans and acne, p greater than 0.05. We found no link between beige jelly beans and acne, p greater than 0.05. We found no link between lilac jelly beans and acne. We found no link between black jelly beans and acne. We found no link between peach jelly beans and acne. We found no link between orange jelly beans and acne, p greater than 0.05. Okay, so they conducted basically 20 of these different hypothesis tests, okay? And one of these, it says we found a link between green jelly beans and acne, p greater than 0.05. So of course, what is the news that gets printed? Green jelly beans linked to acne, 95% confidence, only a 5% chance of coincidence. Okay, and based on this, the way they've done this, do you truly think that green jelly beans, there is a link between green jelly beans and acne? Okay, now, according to the data, the probability of getting whatever we observed in our data is less than 5%. So according to our practice, we would say, oh, we should reject the null hypothesis. But there's also, we have to understand that we've dramatically increased the risk of type 1 error by doing 20 of these tests, right? And basically, if you assume that you've got a 5% risk of committing a type 1 error with each of these tests, and it's not truly 5% every single time because you're using the same data, and so there's some complexities there. But if you assume you've got a 5% risk of committing a type 1 error, and you're going to do 20 of these tests, it's almost like almost certainly you're going to be committing a type 1 error at one of these points, right? Not almost certainly, but just like there's quite a big risk, right? And so if you do a whole bunch of these tests, like here where you have 6 comparisons, or if you had even more groups, you might even do even more comparisons, you greatly increase the risk of a type 1 error. And you might be making some conclusion like this, where you come to this conclusion, green jelly beans linked to acne, but this could end up being just a false positive. Okay, and right, and then the what do you call it? The embedded text says, so we did the green study again and got no link. It was probably a coincidence, but then it says research conflicted on green jelly bean acne link, more study recommended. So that's often what happens in journals is you'll have somebody try to duplicate someone else's findings and then they're not able to duplicate them. Okay. And that's kind of what happens, right? Green jelly bean slander. Yeah, exactly. And that's just what happens when you do a whole bunch of tests. We really we run the risk of type 1 error. Okay, and so this is a phenomenon known as p hacking, and sometimes it's done maliciously, and other times, or I would say a lot of times, people end up committing this kind of error of p hacking just with good intentions. Okay, and it's the idea that, you know, if you just kind of slice your data set in enough different ways, you're almost like bound to find some interesting, unusual thing in your data set. Okay. If you slice your data enough times, right? So you might have spent, so a lot of times this happens when a scientist or research team, you know, they spend a lot of money to collect a bunch of data, right? So they get money, they spend thousands of dollars, they gather some data sets, and then they come back and the conclusion is don't reject the null, it's inconclusive. And they're very disappointed by this result, right? And they say, well, you know what if we only looked at people between over age 50? What if we only looked at people between age 30 and 40? What if we only looked at people with black hair? What if we only looked at people with this? Or what if we only looked at people like that, right? And it's basically what's happening here, right? What if we only looked at this group of people? What if we only looked at this group of people, or did this kind of, and they're slicing it a whole bunch of different ways. And eventually you're almost guaranteed to run into a situation where, oh, okay, you know, if we limit our study to, you know, people in their 20s who grew up in New York but moved to Texas, or, you know, you're looking at some weird group and you go, oh, you know what? We found this interesting link here, okay? And you might be able to get something like that published, but chances are is it could be a situation like this, right? Where you've sliced your data so many times that you end up finding something that looks like there's a link, and then people aren't able to duplicate it, right? So, and that's a real issue. If you just kind of slice your data enough times, you're bound to find something interesting somewhere along the way, right? Okay, so I will recommend XKCD, and the comic is called Significant. There's a bunch of other good comics by XKCD. I like it. Okay, so anyway, what we're going to look at today is when we do ANOVA, we don't do 2 at a time. We're going to compare the means of all 4 groups at the same time. Okay, so with and what we're going to cover is called one-way ANOVA. We compare all 4 group means simultaneously. One test, and therefore our significance level just remains 0.05 or whatever alpha level we've chosen. Okay, and so your null hypothesis will look something like this: that the mean of group 1 is equal to the mean of group 2, and that's equal to the mean of group 3 equal to the mean of group 4. And then the alternative is at least one mean is different. And anytime you have more than 2 groups, it's going to be non-directional. We'll say all ANOVA with more than 2 groups, so 3 groups or more, will have non-directional alternatives. So let me click save there. Oh, you know what? I forgot. I forgot about our view quiz today. So hang on. Let me turn on our view quiz. Double verify what the answers are for the view quiz. Okay, it's this. All right, so your very first view quiz answer for today is the letter D. D as in dog. D as in dog is your first view quiz answer for today. All right, I also have to publish your homework problems and the homework solutions and all of that stuff. So that's on my to-do list for tonight. Okay. Does this make sense? Any questions here as far as I guess the motivation for why we would want to bring up ANOVA rather than just doing a whole bunch of t-tests? All right, so again, what we're going to cover today is one-way ANOVA. This is the simplest form of ANOVA. If so I have dreams, right? If you enjoyed this course and you say, well, you know what, that was great, I want to take more statistics courses or something, you know, I know. I would recommend as a second course, either a course on ANOVA, it's probably going to be called ANOVA/design of experiments, or a course on linear regression. We're going to cover linear regression next week. I would say these are going to be kind of your most practically useful statistics courses and stuff. There's, you know, the statistics, I think we're living in like the statistics golden age because of like so much data stuff. And, you know, there's all these, people are excited about machine learning and AI and all that. And I actually teach courses, you know, related to computer programming for statistics, and it's great. And I do very much enjoy it, but I don't think I could be honestly say that that those things are even more important than these basic tools of linear models, linear regression, and ANOVA. So if you were to take another course, I would recommend your second course be either on linear regression, which is what we're going to learn not next week, on Thursday, or on ANOVA, which is what we're covering today. Okay, so let me pull up our textbook, and I'm going to copy this data table. If I can zoom in. Okay, so I'm going to copy this table of data here. Oh, where did my unpin from start? That's what I want. I don't see it in the start mode. Okay. Somehow it moved. All right. So this is from the textbook. Okay. And so our this is an example from the text, and the question is, this is a made-up example, but we have 12 lambs. So I guess we're on a farm of some kind, okay? And we give the lambs, we put the 12 lambs into 3 groups. We give each of the groups a different diet. and we're going to measure how much weight each lamb gains, okay? And the question is, do the different diets cause different amounts of weight gain? Okay, and basically, if you think about like what's related to weight gain, there's all sorts of things, right? So if you say like, oh, you know, whether we're talking about lambs or people or whatever it is, right? Why are people different, right? Why is that person taller, right? And there's all sorts of reasons, right? All sorts of things that come into play as far as like why one person is taller and one person's shorter, right? There's just individual genetics, there's nutrition things, there's you know, maybe and you can say, you know, certain you know, certain genders or sexes tend to be taller or shorter, certain perhaps races or ethnicities tend to be taller or shorter, et cetera, et cetera, et cetera. There could be all sorts of things at play, right? And so as far as one way ANOVA goes, and looking at the diet, the lamb weight gain, we're going to try to say what are the reasons for why the in our data, we have 12 different lambs and the lambs gained different amounts of weight. Why are the lambs gaining different amounts of weight, right? So this is kind of the analysis of variance here. Okay, the variance part is basically saying the different lambs gain different amounts of weight. And we want to attribute the reason for why they're gaining different amounts of weight. Okay, and basically we're going to say, we're going to peg the source of variance to either, we're going to look at perhaps the different diets cause different amounts of weight gain. Or maybe cause is too strong of a word. The different diets are associated with different weight gains. And then just individual differences between the lambs, right? So just when you're looking at different individuals, individual differences between lambs, right? So you could have given all the lambs the same diet and you still would have gotten different amounts of weight gain just because the lambs are different, right? There's one lamb that just keeps eating and gains a lot of weight, and there's another lamb that eats less and doesn't gain as much weight, right? So there's always going to be just individual differences. Okay. And so what we're going to do is we want to kind of figure out why some of the lambs gain different amounts of weight. So first we've got to figure out some summary values, right? So here some summary values are provided, okay? And you're going to need the summary values, okay? And we're also going to need to kind of calculate one of the important summary values is going to be the grand mean. You know, here I also have I plotted the data. Let me see if I can, how big do I want this plot? Okay, put this here. Copy this. So here's a plot of the data, right? So I have, so, 8, 9, and 16, and that's plotted right here, 8, 9, and 16. And then we have 9, 16, 21, 11, 18. So 9, 16, 21, 11, and 18. Okay. 18 is up here. And then we have 6, 10, 17, and 15. Okay, so here's a plot of the different amounts of weight gain. All right, and here each group mean is shown in red. This is the group mean. So this is Y bar for group 1. This is Y bar for group 2. And this is Y bar for group 3. Okay, and so group 1 has a mean of 11. Group 2 has a mean of 15. And group 3 has a mean of 12. And that's what I've plotted these red lines. Okay. Okay. And then what we're going to have, what we have to do is we have to calculate the grand mean. Which is basically the mean of all values in our data. Now, we have the raw values. We have all 12 raw values. And so the grand mean, we use the symbol Y double bar. And we can just add up all the raw values, add up all the values. And we're going to divide by the total number of values. All right, and so if you go through and you add up all of these numbers, you're going to get 156. And you can divide by the total number of values. We have 12 observations. And you would get a grand mean of 13. And this grand mean is shown, and this is the large blue line. This is the grand mean. Y double bar is equal to 13. Okay, now, oftentimes you do not have the raw values, okay? In many circumstances, we only have summary values. So basically you only have the lower half of the chart, okay? So you might only have the summary values. You might only have an n, a sum, a mean, and a standard deviation, or maybe just the n, the mean, and the standard deviation. You can get the sum back by multiplying the n by the mean, right? So in many cases, you only have summary values. So you have to, you can still calculate the grand mean. Is found this way, okay? The grand mean is you take each group mean, Y bar, for group I, and you're going to multiply it. You're going to multiply the group mean, Y bar I, by the group size, n sub I, okay? And then we're going to divide by the sum of the groups, okay? So in our case, we're going to take kind of our first group, which had 3 observations. We're going to multiply it by the group mean of 11. We go to our second group, which has 5 observations. We multiply it by the group mean of 15. And we go to our third group, which has 4 observations with a group mean of 12. And we're going to divide by the sum of the group sizes, which is 3 plus 5 plus 4, right? These are the number of observations, and that's going to be 12. And so if you do this, you get the same value as we should, and we're going to get the same thing, 13, okay? But this is just kind of the idea that if you didn't have the raw values, which is often the case, because when you look at a study, they might have like hundreds of observations, and they don't want to print out the whole table of every single observation that they recorded. So they might just show like some kind of summary values, okay? And in that case, you can still get the grand mean by doing wide double bar, okay? Now let me just do a warning here because I see this mistake made often, okay? Do not do, this is what you do not want to do, is you do not want to take the mean of group means. Which is going to be, you're going to do like 11, the group mean of 11 plus 15 plus 12 and divide by 3. Okay, this is wrong, right? If you do 11 plus 15 plus 12, you're just taking the mean of your group means. That will give you the wrong answer. You need to basically multiply them by the group size to kind of account for how many observations there are. Okay, so here's our picture. This is the, we have the 12 individual dots, the 12 individual lambs, separated into 3 groups, group 1, group 2, group 3. Here is the grand mean shown in blue, and we have the group means shown in red. Okay. All right, and so let me put this chart down here again. All right, and so let me just discuss a little bit of notation here. So as far as notation, the individual values are indicated as Y, I, J, okay? I is the group number, and J is the value within the group. Okay, so this number 8 is going to be Y1. All right, over here. This is Y11, okay? It's in group 1, first observation group 1. This next number is Y12. It's the group 1, second observation, and 9 is Y13. It's the first group, third observation. This would be Y21, Y22, Y23, Y24, Y25, so on and so forth, okay? So basically, yeah, Y24 is the 4th value in group 2. Which in this case is equal to 11, okay? Y bar I is the mean of group I. Okay, so Y bar 2 is the mean of group 2, which is 15. Okay, and so if we talk about, what is the total variance? Total variance for all observations. Okay, this would be equal. So this is the S squared value for all observations. This is going to be each individual value minus the grand mean squared divided by total observations minus 1. Okay, and so we would go through and we would do, 8, the grand mean is 13, right? Okay, so it would be 8 minus 13, oops, 13 squared, and we would go through 16 minus 13 squared, and 9 minus 13 squared, and go to the next column, 9 minus 13 squared, so on and so forth until you get to your last observations, 6 minus 13 squared, okay? And then we would divide this by 12 minus 1, okay? The numerator, this numerator up here, is known as the sum of squares. It's the total sum of squares, which kind of makes sense, right? Because we're squaring a whole bunch of values, and if we add them all up, it'd be our total sum of squares. So the numerator, before we divide by the total number of observations minus 1, the numerator is called the total sum of squares. I don't know if you've heard that term before, sum of squares, the total sum of squares, or we might call this SS total, okay? And sum of squares total, SS total, we can also just symbolically write it like this. You have a double summation. And the idea here, so you're going to take each individual value, subtract off the grand mean, square it, and the sum j means add up all for all j observations in a group. Add up the squares for all j observations in a group. And the sum over I means repeat this for all repeat and add for all I groups. In our case, we've got 3 groups. Okay, how do we feel about that? Okay, I hope it's okay. All right, so what we're trying to do is we're going to take this total sum of squares and we're going to try to like break it up. We're going to try to break it up into a few parts, right? We want to say, okay, how much of it is due to the group difference? How much of it is due to the individual differences, right? So let's just take a look at, this first little lamb here, okay? This first lamb gained 8 pounds, okay, on diet 1. What did I do? So don't want to copy this. Let's get this first lamb here, and still I want this picture as well. Okay, so let's look at this little lamb. All right. Okay. So this lamb, Y11, gained 8 pounds on diet 1. Okay. And we say it contributes how much? It contributes 8 minus 13 squared, or that's 25, to the total sum of squares. Okay, so this lamb contributes kind of 25 square pounds, whatever that is, 25 square pounds to the total sum of squares. And what we want to do is we kind of want to decompose the total sum of squares into differences between groups and just individual differences. Differences between groups. And we can think of the differences between groups as basically how much is each group different from the grand mean. How much each group's mean is different okay? And we also want to do individual differences. Which is going to say that the lamb itself, okay, each individual lamb is different from its own group. So even when you look at all the lambs on the same diet or within the same group, you still have differences there, right? So each individual shows differences from its own group average. Okay, so basically we're looking at this 8 and we're going to say okay, we look at this and we say, all right, the group mean all right, so the grand mean is 13 and the group mean is 11, okay? And so diet 1 already has a mean that's lower than the average. And then on top of that, this lamb itself has a, let's my control here. We look at this individual lamb is down at 8, which is way down here, okay? And on top of that, this individual lamb is different from its own group, right? So this is the individual right here at 8 pounds, okay? So we'll look at, the sum of squares between groups. We can say, all right, let's look at all of the individuals in group I, okay? And each of these, if we look at all 3 of them, they're going to have the same kind of difference for its group mean versus the grand mean. Because for all 3 individuals in this group, the group mean is 11 and the grand mean is 13, okay? So each group has a mean yi bar, okay? Which is different from the grand mean. Okay. And all individuals, all ni individuals in the group will have the same group mean. Okay, so the total sum of squares, or I'd say the sum of squares due to groups is going to be basically y bar I minus y double bar times n sub I. Okay, we're going to take each group, and then this is the double bar, take each group mean and its squared difference, and we're going to multiply by its the total number in that group, n sub I. Okay, and then we look at the sum of squares within a group. okay? And here we're going to do this basically for all individuals. Basically, each the formula is we're going to do this for all individuals within group, and we're going to do it for all groups. We're going to take each individual value and subtract off its own group mean and square it. Okay, and we're going to say just even within a group, right? So you say, well, why, how do we end up with all of these lambs gaining different weights, right? I gave all three of these lambs, I gave them the same diet. How are they ending up with different amounts of weight gain? Well, it's just because everyone's different, right? Every lamb is different. So even though you give all of these lambs the same diet, some are going to gain more and some are going to gain less, right? And so that's the individual differences. That's the sum of squares within a group. And so we're going to just say, okay, each individual, compare it to its own group, they're still different. We're going to take those differences, square them, add them up for all the individuals within a group, and we go, whoa, you know what, we also have 3 groups, so we got to do it for all 3 groups. So we've got individual, I'm not able to write right now, individual Yij, okay, has a value different from its own group mean. So we square that. Which is y bar I, okay? And then we're gonna square those differences. And add them for all individuals in the group. Chat. Oh boy. All right. It says for the sum of squares between groups, what is the n sub I? N sub I is the number of observations in group I. N sub I is the number of observations in group I. Okay, so this is number of observations in group I. Okay, so square the differences for all values within the group. And sum and repeat and sum for all groups. Okay, I know I'm showing you a whole bunch of formulas and stuff. I think, well, maybe it's fine, but I think it will make a little bit more sense if we just plug in numbers and add this up, okay? We're gonna plug in some numbers and add this up. All right, so let's go ahead and do this. Let's just do this for one of the diets, and maybe it'll make sense. I hope it makes sense. Okay. All right. So where am I? All right. So I want this picture again, and I want my data table. Okay, so here we go. All right. Let's just take a look at group 1. All right. So here's so what we're going to find is the relationship is the sum of squares between groups plus the sum of squares within the group will equal the sum of squares total. Okay. All right. So again, we have a grand mean of 13. All right. So our grand mean is 13. Let's look at group 1. Group 1 has 3 lambs. And the gains are 8, 16, and 9. Okay. So the contribution to the total sum of squares is, again, the sum of the individual values minus the grand mean squared, right? We're going to add this up. Okay, so if we do this, we're going to take each value. We got 8 minus 13. We're going to square that. We'll take the next value, 16 minus 13. We'll square that. And we'll do the last one, 9 minus 13. And we'll square that. I'm just doing it for one diet. I mean, we could do it for all 3 diets, but then it would be, it would take a long time. So I'm just doing it for one of the diets. And so 8 minus 13 is 5. We square that. We get 25. 16 minus 13 is 3. We square that, we get 9. 9 minus 13 is 4. We square that and we get 16. And when you add up 25, 9, and 16, you get 50. So this is kind of diet 1 contributes 50 to the total sum of squares. Okay, happened here. All right, and then, all right, so then let's look at the sum of squares between the groups. Okay, sum of squares between is we're going to take basically the group mean, y bar I, so the mean of group 1, and we're going to say, well, how different is group 1 from the grand mean? Okay, well, group one has a mean of 11. So group 1 has a mean of 11, and it's different from the grand mean by 13, right? So we take this and we're going to say, all right, we have a difference of 2, and we're going to kind of take these differences and we're going to square them, and we've got 3 observations. So we're going to do this difference of 2, we're going to square it and multiply it by 3. Okay, so group 1, its mean is 11, the grand mean is 13, so that difference is 2, and we've got 3 observations in group 1. So we're going to do 3 times 2 squared, or 4, and the sum of squares between is 12. Okay, and so I'll draw this in kind of a red circle. Oh, here, you know what? Let me take like a light blue, and I'm going to draw, right? So we think about the total sum of squares. The total sum of squares is how different is each individual value from the grand mean. So we're going to kind of okay, so from the grand mean, this guy is at 16. This is 3 away, so we square that. And then this observation down here is this far away. And this observation down here is this far away, right? So these blue arrows kind of show us the total contribution to the sum of squares. Right? And then lastly, so that's a total sum of squares, and then we've got the sum of squares within. And we're just asking how different is each individual from its own group? Because that's still part of the issue, is that the individuals end up being different from its own group. So here within the group, we're going to take each individual value, subtract off the mean of the group, okay? We're going to square it, and then we're going to add this up for all individuals here, right? So here the group mean is 11, and we're basically saying, you know what, let's look at, what color can I use here? Here, I'll use purple. And we're going to say, you know what, this guy is like way higher than its group average, right? And so here I'm drawing lines from the group mean right here. We're saying how different is each individual from the group mean? So The differences we've got there is this observation is 8, and its group average is 11. So this distance here is 3. The next observation is 16. The group average is 11. So its difference is like 5, okay? And we're going to square that. And then the last observation has a value of 9. The group average is 11. We're going to square that. So we get 9, 25, and 9 minus 4. Okay. So you add this up, 9 plus 25 plus 4, you get 38. Okay. And as promised, we see that 12 plus 38 is equal to 50. Okay, sum of squares within, or sum of squares between, plus sum of squares within is equal to the sum of squares total, which is 50. Okay, and you could do this for all 3 groups and you'll find the same relationship, okay? So if you do this for diet 2 and you did it and you do it for diet 3, you're gonna find that the sum of squares between and the sum of squares within will add up to the sum of squares total. Okay, sorry, there's been a, okay. So yeah, where did the 11 come from? Sorry, the 11 is the mean of diet 1, right? If you take 8 plus 16 plus 9, 8 plus 16 plus 9 add up to 33. 33 divided by 3 gives us a mean of 11. Okay, so the mean of group 1 is 11. Okay. Is that all right? Sum of squares total, sum of squares between, sum of squares within. Okay, let me go ahead and give you your second view quiz answer. Okay, second view quiz answer for the day is C. C as in cat. C as in cat. C. That's your second view quiz answer for today. All right, so again, what we're trying to do, and we have successfully done for this first group here, is we're trying to do an analysis of the variance, right? So the total, it's kind of like this, right? We say, why did the lambs gain different amounts of weight? Okay, and the SS total basically just says, everyone's different, and that's why, right? Everyone's different. So some people gain more, some people gain, not people, the lambs, right? But whatever question you have, you can that can be your answer, right? Like like if a child asks you a question, like why are some people tall and some people short, right? And you can just say, well, everybody's different. Okay, and that's the truth. Everybody's different, right? Why are there differences? And it's just that everyone's different. Okay, but we can also try to break it down and attribute it and say, well, you know what? It's not just that everyone's different, but it's also that, some people have different diets, and that contributes to why people end up being taller or shorter, or the lambs have different amounts of weight gain or whatever it is. Okay, you can also, you could find some other attribute, right? Some people have different blah blah blah, and or they live in different countries and blah 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 blah, and whatever it is, right? And you can try to attribute part of the reason why people are different, or the lambs are different, or whatever it is different, to some kind of grouping variable. And here we're trying to take this total number of variance. So rather than just waving our hands and saying everybody's different, is we're taking, all right, we have a measure for variance, right? And it's the sum of squares total. How different the actual values, how different are they from this mean of everybody? That's the sum of squares total. And we're breaking that down. We're going to say, these values, these 3 values contribute 50 points towards the sum of squares total. And we can actually break that down and say 12 of them come from the fact that they're in this one group, right? And 38 of them come from the fact that even within the group, they're different, because we're taking the difference between how each group from the grand mean, how different the group mean is from the grand mean. And we're also looking within a group and saying, how different are the individuals from its own group mean? And so we've broken down the 50 into two parts, 12 and 38, right? And we can do this for all of the groups. And what we can do is we can then arrange all of these numbers into this big, what we call the ANOVA table. And so let me try to write this. So I'm going to write across the top, I've got source of variance. And then the next column is our favorite thing, the degrees of freedom that shows up everywhere, right? All right, and then we're going to have the sum of squares as our next column, which we'll call SS, all right? And then later on, we'll talk about the mean squares, and then we'll have an F ratio. All right, so the source of variance, we're going to say we've got between the groups is one source of variance. And then we're going to have another source of variance, which is within the groups. And let me go ahead and draw a line across, and then we'll have the total. All right. So within groups, this is also known as our residual variation. And as in, like, you can't really get rid of it. It's just kind of stuck. All right. So the total degrees of freedom is n dot minus 1. This is the notation our book uses. N dot is basically the total number of observations. Minus 1, number of observations minus 1. I'll just do a side. N dot is equal to the sum of the ni's. Total number of observations in the raw data. Okay. The degrees of freedom within the groups is I minus 1, which is the number of groups minus 1. And then the degrees of within groups degrees of freedom is n dot minus I, number of groups minus, number of observations minus number of groups. Okay, and you can see that if you add this I minus 1 plus n dot minus I, you're going to get n dot minus 1, right? The formula for the sum of squares is we're going to do n dot I times, each individual value, each group's mean, y bar I minus the grand mean. We're going to square that, and we're going to add this up across all groups. And then I'm going to put in a different number here, or a different formula. The sum of squares within is equal to, earlier we said we're going to do a double sum. We're going to take all the individual values within a group, yij minus y bar sub I. And we're going to square that. We're going to do it for all the individuals within a group, and we're going to add it up for all groups, right? This we can actually simplify into this quantity, n dot I minus 1 times si squared, okay? And why is that? Okay, why is that? Is if we think about the variance of group I, what is the variance of group I? Okay, the variance of group I will be si squared, and this is just the formula for the variance. We're going to take each individual value, subtract off the group mean, square it, and divide by the number of observations minus 1 in group I, right? So this is just the definition of variance. And what we're going to say is, well, you know what? Look at this, okay? This part right here, this part matches this part right here, okay? And therefore, I can say, I can just replace this entire thing with SI squared times n minus 1, right? So with just a little bit of algebraic manipulation, we can say n dot I minus 1 times SI squared is equal to the sum of Yij minus Y bar sub I quantity squared, right? And so we're going to plug this thing into here. And so this ends up being kind of a simplified version of this. And this does not require the raw values. We can just use summary values. All right, so the sum of squares within a group using summary values only is going to be the number of observations in group I minus 1 times the variance of group I. Okay. If we wanted to do the SS total, this would just be the SS between plus SS within. We can also calculate it if we have the raw individual values. And that would just be the sum of each individual value, Yij minus the grand mean, squared, added across all values within a group, repeated and added up across all possible groups, okay? I don't know how comfortable you guys are with all of this double summation with the different subscripts of I and J. All right, some of you guys are okay with it. Some of you are like, oh gosh, I hate all of this stuff. If you can handle these two formulas here, then we're in good shape, okay? Don't worry about this bottom one here, okay? So these two formulas, there's only one summation sign. And if you can handle those, then you're in good shape, okay? The mean squares, okay? This is always the sum of squares divided by the degrees of freedom. So we're going to do sum of squares between divided by the degrees of freedom for between. And here we have the sum of squares within divided by the degrees of freedom. And here, if you do the sum of squares total divided by the degrees of freedom, this is just equal to the total variance. Right? This is the total sum of squares divided by the number of observations minus 1. That's just your total variance. Okay. And then the F ratio, there's no F ratio to calculate here. There's no F ratio to calculate here. But the F ratio is done with taking the mean squares between, and we're going to divide by the mean squares within. Okay, so we're going to do mean squares between divided by mean squares within. All right. Is that okay? All right, so let me copy this table onto the next slide and let's fill in some numbers here. Let me put this up here. Let's take, whoops, oh shoot, I didn't want to do that. Oh, okay, well, maybe. I don't know how to zoom on my computer. Okay, well, that's good enough. Ah, what's going on? Oh, by magic, it worked out. Okay, please don't go crazy on me here. All right, let's plug in the numbers we have. Let's fill this out here. Please don't break on me, computer. Okay. All right, so let's all right, so we've got all right, source, degrees of freedom, sum of squares, mean squares, F ratio. All right, so we've got between, within, and I'll just write total. All right, so the degrees of freedom here is the number of groups minus 1. We have a total of 3 groups, so my degrees of freedom is 2. Okay, within, well, let's do total degrees of freedom, right? So we've got 12 observations. 12 observations minus 1 is 11. And then basically we just need to know that these two things have to add up to each other. So we can just plug in a 9 here. Okay, we can also do total observations. 12 minus number of groups minus 3. 12 minus 3 is also 9. Okay, sum of squares. Let's do this. Okay, we're going to take each group, the number of observations in each group. So this first one, we have 3 observations. And we're going to take the group mean of the first group, 11, minus the grand mean, which is 13. We're going to square that. We'll go to the next group. We have 5 observations. So again, if we had forgotten, the grand mean is 13. 5 observations in the next group, the mean is 15. We're going to subtract off the grand mean. We're going to square that. Let me move over this, delete this mean squares. I'm going to run out of space here. Okay, and then we'll go to the third group. We have 4 observations. The grand mean is, I'm sorry, the group mean is 12. The grand mean is 13, and we'll square that. Okay, so here I've got 3 times 11 minus 13 is 11 minus 13 is 2. Negative 2 squared is 4. Okay, so I'm going to do 3 times 4 plus 5 times 15 minus 13 is 2. 2 squared is 4. Plus 4 times 12 minus 13 is 1. 1 squared is 1. Okay, so I've got 3 times 4 is 12. And 5 times 4 is 20. And 4 times 1 is 4. This adds up to 36. This is my sum of squares. Let me put in squares here. Okay, let's do the within, sum of squares within. Okay, we're going to take the number of observations minus 1 times the group standard deviation squared, or group variance. Okay, so here I've got 3 observations minus 1. So 3 minus 1 times, we're going to take the standard deviation, 4.359, and we will square that. We'll do this for all 3 groups. We've got 5 minus 1 squared times the standard deviation, 4.950 squared, right? And then the last group, 4 minus 1 times 4.967 squared, okay? Here, let me go ahead and pull up my calculator. We can punch all of this in. Why do we square 5 minus 1? Did I square 5 minus? Oh, we shouldn't. That was a mistake. Thank you. Thank you for catching that. That was a mistake. We should not be squaring. What did I do? We should not be squaring 5 minus 1. It's just 5 minus 1. Just shrink my eraser, and I need to. Thank you. It's a good catch. Okay. We do not square that. Okay, so 5 minus 1. Okay, so Where did I put my calculator? My calculator is right here. So I'm going to do 3 minus 1 is 2 times 4.359 squared plus 5 minus 1 is 4 times 4.95 squared plus 4 minus 1 is 3 times 4.967 squared. Okay. 210. 210. It's here it shows 210.025, but that's because we have some rounding issues with the standard deviation. I mean, if I included it, we wouldn't be too far off, but the number's 210 here. Okay, and the sum of squares total would be 36 plus 210. And we would get 246. All right, so my mean squares is going to be 36 divided by the degrees of freedom, in our case 2. So we're going to get 18. And then over here, I'm going to get the sum of squares 210 divided by the degrees of freedom 9. And 210 divided by 9, 23.333. Okay, and then my F ratio is going to be 18 divided by 23.333. It's the mean squares between divided by mean squares within. Okay, so my F ratio, oops, 18 divided by 23.333, 0.771. That's my F ratio. Maybe I'll move this over. All right. Any questions? Yeah, thank you guys for catching that mistake where I squared 5 minus 1. I should not have squared it. It's just n minus 1, not n minus 1 squared. Okay. So are we good with getting the sum of squares, the mean squares, and the F ratio? Okay. Oh, and if we if I just did this 246 over 11, that would I love when my calculator just does stuff like this. 22.3636. That's the total variance. Okay. That's the total variance. But anyway, here's our mean squares, our F ratio, sum of squares, all of that. Okay, any questions on how we arrived at any of these values or numbers? You can definitely expect to be asked some kind of question like this on the quiz this coming week, where, give you basically a kind of I will probably just give you the summary table. I won't even give you the raw values, the summary table, and then I'll ask you to, what's the sum of squares between, what's the sum of squares within, what's the F ratio, things like that. Okay, well, I will go on to the next slide then. Okay, so when we do this, let's kind of, so we talked about filling out this table, but this is all in the context of doing a hypothesis test. Okay, so let's talk about what those hypotheses are and how we would go about getting a p-value and all of that. Okay, so so in one way ANOVA, our null hypothesis, okay, I think we already showed this, would be that the means of all three groups are equal. Okay, all three diets basically result in the same mean weight gain. That's what the null hypothesis is saying that, you know, the diet really doesn't matter. They're all going to just gain on average the same amount of weight. Okay, of course, individually, some lambs are going to gain more and some are going to gain less, but really it doesn't matter if you give them corn or barley or I don't know what they give to lambs. So actually I have no idea. Grass, what do they give? Does anyone know anything about raising sheep? I don't know. Okay. All right. And then the alternative is it's non-directional, and we're just going to say at least one of the means, one of the diets has a different mean weight gain. Okay. So from the previous page, our F ratio is 0.771, okay? And I can't remember, did I give you an F table? Reference tables, do you guys have an F table? Let's see. Oh, you do. Critical values of the F distribution. I only gave you the first 2 pages. Okay, that's all right. So our textbook has this very like elaborate F table. Most F tables are much less elaborate. Okay, so our F statistics come with our test statistic F has a numerator df and denominator df. And it's basically, you know, the F ratio is I'm like stumbling over my words today. The F ratio is the mean squares between divided by the mean squares within, right? So the mean squares between, how many degrees of freedom were associated there? 2. The number that went on the top, we had 2 degrees of freedom. How many degrees of freedom did we have on the bottom? We had 9, okay? So we've got numerator df is 2, denominator df is 9, okay? And what we're gonna do is we can go to our table and we're gonna go to numerator degrees of freedom 2, denominator degrees of freedom 9, and we're gonna look for our test statistic 0.771, okay? And what we find is that it's less than this number, 1.93. Okay, so I'll copy this part here. Now, I would say most F tables don't look like this. You can look up F tables online, and honestly, to be honest, we really just throw things into the computer and ask for a p-value anyway. But here we have numerator degrees of freedom 2, denominator degrees of freedom 9, and we're looking for 0.771 is less than that first row, 1.93. Okay, it was less than that first value. So the corresponding tail probability is going to be greater than our column heading 20%. Okay, and I think that's I think that's comfortable with you guys, right? All right, so that's what we have. So our F value, our tail probability is going to be greater than 20%. This is going to be our, basically, you're going to have non-directional hypotheses. So this tail probability is our p-value. Our p-value is greater than 20%. And if let's say alpha is equal to 5%, we would say do not reject the null hypothesis. Okay, and we would say a lot of students were tripped up by all the conclusions, and I think it's because we have all of these double negatives, and the wording admittedly is it's like, I get it, it sucks. So we do not reject the null hypothesis, right? So our conclusion, do not reject the null. So what does that mean? Okay, anytime you do not reject the null, you're going to say we do not have evidence of what, right? We do not have evidence, ... So do not reject always goes along with we do not have evidence. What do we not have evidence of? Okay, we don't have evidence of the alternative. We don't have evidence of the alternative. We do not have evidence that at least one diet has a different mean weight gain. Okay, we do not have evidence basically to support, I'll say do not have evidence for okay. Yeah. Well, yeah, we do not have evidence to conclude the alternative. It doesn't mean that the alternative is definitely false or that the null hypothesis is definitely true, but we're going to have to say, we do not have, and it just might be that we didn't have enough, right? We don't have enough evidence to say that at least one diet has a different mean weight gain. Okay. So it doesn't, again, do not say we have evidence that all three diets result in the same mean weight gain, right? So do not say we accept the null hypothesis. Do not say we have evidence. So just because we don't have evidence against the null doesn't mean we have evidence that the null is true. So we do not say we have evidence that all three diets result in the same mean weight gain. Okay. Let me just throw in a slide here. We went through all of that work, and yeah, zoom in here. This is how we would go about doing our test in. So you would enter all of the numeric values in a vector y. You would enter all of the group information in basically a factor here. Okay, so I have group. So basically, the observations 8, 16, and 9, those three observations correspond to group 1. And then the next 5 observations, 9, 16, 21, 11, 18, go into group 2, 2, 2, 2, 2. And the last 4 observations, 15, 10, 17, and 6, go into group 3. So, I enter y into my data. I enter the group information. I put them together in a data frame. I'm going to put in, column Y and group. We'll call that my data dat. And then I create a linear model. Don't worry, you're not going to be tested on this, but I just want to show you that this can be done quickly in R, right? So Y tilde group, this is explain the Y variable using the group variable. The data is found in the data frame dat. And then we can ask for the analysis of variance, AOV, of the model. And it kind of gives us, and it says we have 33, sum of squares for the group is 36 with 2 degrees of freedom. The residual sum of squares is 210, and the degrees of freedom is 9. And then you can get the resulting ANOVA table here with this. When you ask for the summary of the AOV of the model, this is pretty much the exact same table that we produced a few slides ago, right? And basically we spent, this first whole hour and a half going over how we go about calculating this, and just with a few lines of code, we have the results here. So I'm going to go ahead and I'll throw this into one of the slides if you're interested in how to go about entering or doing something like this in R. So I'll just throw this in here. I apologize. There was a question. It said, would we have evidence to support the null hypothesis be wrong? Yes, you cannot say we have evidence to support the null hypothesis. It's always, we don't have evidence against the null. Okay, so you think of like a criminal trial. It's always the verdict is either guilty or not guilty. Okay, the jury will never say, we the jury find the defendant innocent. Okay, that's not a conclusion that they can make. The evidence either leads them to a conviction, rejecting the null hypothesis, or it doesn't. Okay, and just because the jury says not guilty doesn't necessarily mean innocent. Just means there wasn't enough data to reject that null hypothesis. There wasn't enough data to convince the jury that the defendant is not innocent. So, so you say, yes, you'd say we fail to reject the null. Okay, we fail to reject the null. That is correct. We fail to reject the null, but failing to reject the null is not the same as proving that the null is true. Okay, I've got just a couple minutes left, and I want to just mention other forms of ANOVA. So as far as our class goes, you will only be tested on one-way ANOVA. Okay, so I will just write that. You will be tested only on one-way ANOVA, which is what we covered today. But there are other forms of ANOVA, okay, or there are more complicated forms of ANOVA. Okay, so you have, what's called like a randomized block design. We have a factorial ANOVA, et cetera, et cetera. Okay, so I just want to kind of mention the randomized block design. Okay, and there is a question. It says, will we have a quiz this coming Monday? Yes, you will have a quiz. Okay, and that will be the last of the quizzes. I know it's like quiz every week, and then you will have a final exam next week as well. Okay, so this week, today I covered chapter 11. On Thursday, I will cover chapter 12. You'll have a quiz this weekend on chapters 11 and 12, and then on Tuesday we'll have a review. And then on Thursday, you'll have the final. And that will be it. That will be it for the class. I hope you've enjoyed it. I miss being in person, but I've had fun. I've had fun teaching. Well, I always do. So, but anyway, is week 4 lab also our last lab? Okay, so I'm actually going to assign another lab, but the last lab is not going to involve any R, right? And I know this lab 4, like the R programming is like, it's like, oh man, every week it's like gotten harder in this last one. Like the R program is fairly challenging. So the last lab 5, no R involved. Okay, so it's not the last lab. Okay, so you got 5 quizzes. You're gonna have 5 labs, and same schedule as kind of we've been having. But lab 5 is not going to involve R. And you'll see that on Thursday. Okay. Have you given the third view quiz answer? I have not. Oh, thank you. Thank you for reminding me. Third view quiz answer is A. A as an apple. A as an apple. Okay. A as an apple is third view quiz answer. Oh, I'm going to run out of time here. All right. So let me just do a quick contrast. All right. So we can have what's known as the kind of the effects model. All right. Okay. So for one-way ANOVA, the effects model looks like this, right? We're going to say that each individual y value, yij, is equal to mu plus the effect of being in treatment group I plus the individual values, right? So we're going to say each value yij, I'm going to go a couple minutes over and I'm sorry, is equal to the grand mean mu in the population. Grand mean is population grand mean mu plus the population effect of being in group I and that's tau sub I treatment group I plus individual or residual variation. Epsilon ij. Okay. And the null hypotheses are written this way. Tau 1 is equal to tau 2 equal to tau 3, and they're all equal to 0. Basically, being in treatment group I has no effect. So this is the effects model. Okay, and then the alternative is at least one group has an effect. As a non-zero effect. Okay, so that's the one-way ANOVA expressed in the effects model. And you can also have the randomized block design. And the randomized block design just makes it, we add more letters here, okay? We got Y, I, J, K. And we've got mu plus tau I plus beta J plus epsilon ijk. All right, what's with all of these letters here? Okay, so we're going to say each value equals grand mean plus, and this is again population grand mean. Okay, so this is the effect of being in group I. That's tau I plus the effect of being in blocking group. So you have two groupings, being in block J. So that's beta J plus individual variation. And there ends up being two hypotheses to test. So 1 is going to be tau 1 equal to tau 2 equal to tau 3, all equal to 0. And then the other one is beta 1 equal to beta 2, that all of the blocking groups have no effect. Okay, so what is this? What is the deal with blocking groups? All right, question. We don't need to know this for the class. those questions are always a little bit always hurt my feelings a little bit, but that's okay. So the answer is you will not be tested on this. So that is correct. You will not be tested on this, but do you not need to know it at all? I mean, I think it's useful, and thanks for trying to save that. You know, it's still very interesting. I appreciate the save attempt there. But yeah, I think it's worth mentioning, and I know I'm going a few minutes over in class here, but yes, I will not test you on this. I just kind of want to mention this and just kind of give you a glimpse into kind of the power of ANOVA, right? Because so far we've just done this one-way ANOVA thing, which seems fairly simple and rudimentary, but really you can do so many cool things with ANOVA. And so just kind of one example, right, is you might want to use a blocked design if there's like a secondary factor that has an impact on whatever it is you're recording, but it's not really the thing that you're particularly interested in, okay? So let me just kind of jot this down real quick and then I'll let you guys go, all right? So use a block design. If there is kind of another factor that impacts the response or recorded variable. Okay, so so for example, let's say, I don't know, you're testing out like 3, I don't know, fertilizers or something. We're gonna see like and you've got like this lab, right? And there's like a window here. All right, and so we say, you know, you're gonna grow plants in the office. Okay, and you've got fertilizer A, fertilizer B, and we'll have control. Okay, and with the window, this area of the office gets lots of sun. This area gets some sun, and this area gets little sun. Okay, so this would be a bad design for the experiment. Would you would put all plants with fertilizer A in the lots of sun zone. And then you would put all plants with fertilizer B in some sun, and all control plants in little sun. Because maybe at the end of the study, fertilizer A grows the tallest. Fertilizer and control grows the least. Okay, and the problem is we don't know the reason. We don't know if it's because they were in the lots of sun or if they were in because we got fertilizer A, okay? We can't separate the effect of fertilizer A from the effect of lots of sun. We would say these effects are confounded. Okay. Okay. And you can have a total random design. Okay, total random, you just kind of randomly say, you know, we're going to mix them up, put some fertilizer A here, some fertilizer B there, some fertilizer control over here. But it's still possible because of randomness that more fertilizer A ends up in the lots of sun group, okay? But with random, you can still end up have too many fertilizer A and lots of sun. Okay, and you can still end up seeing some kind of effect and you're not sure, okay? So the randomized block design you would make sure you get kind of like 3 from each category, 3A, 3B, and 3C in each zone of sun. Okay. And then at the end of the study, if you see that consistently in all 3 zones, fertilizer A plants grew the most and the control plants grew the least, then we can conclude that fertilizer A has this effect, right? Has the effect of causing the plants to grow the most, okay? But you need to kind of design your experiment in such a way to kind of get these results. And it seems very kind of obvious and intuitive as far as, you know, setting up fertilizers and stuff like that. But the truth is when people think about doing studies is sometimes they don't always think about these things. And, you know, they end up, you know, starting a study with a poor design. Maybe they didn't consult a statistician, but, you know, they just said, hey, let's do an experiment. They spend lots of money to collect the data. And at the end, they have trouble separating the effects of these different kind of confounding variables. And so, you know, I always kind of course, I'm biased and I have this opinion, but I think people who design experiments should always kind of consult a statistician to kind of make sure that the design of the experiment is going to result in the most useful information that we can extract, right? And so again, if this kind of stuff interests you and you see the possibility of participating in research or doing some kind of experimentation in the future, I would recommend taking a course on experimental design in ANOVA in the future there. Okay, anyway, that's it. And again, yes, you will not be tested on this stuff, so don't worry about it. We'll end here for today. Sorry for going a few minutes over. Thanks for your patience and sticking around. And we'll see you guys on Thursday. So have a good night.